Okay, welcome back to our second coding lesson. Last time, this is where we left off, where we had just done some analysis with this data on US colleges and universities. Now we want to start a new project for our second module, technically module 3, but the way to do that is after you've saved your code on your previous project, go up here to this little drop down arrow. This will list all of the projects that you have worked on recently in R. And we want to start a new project, so I'll click new project, and then it's going to ask, do you want to save your current workspace? This is saying, do you want to save all of these objects into this folder that you had for your previous project? That way, next time you open it, we can just open these up again and you can just take off with your code again without having to reload in the data. So as long as your data is not too ginormous, typically yes, sure, that'd be good. And then it will give us the opportunity to create another new project, new directory, new project. We just need to know where to put it. I want to put it back in my tutorials folder, just like my previous project, and click open. I'm going to name this one smoking because that is, I'm going to do smoking tax just to give it a little bit more of a description, because my data is going to be about smoking rates. Yours is going to be for your next homework assignment, which is going to be using data from minor league baseball. So call it whatever helps you remember what this is when you see it in your folders, and then click create project. It will close your previously opened project and start a new one. Just like last time, we need to click this button for a new R script so that we can get started. Okay. Step 2, we go to our Canvas page, module 3, and download the data that you need. I'm going to download smoking and work with this data. For your homework, it will be the baseball data. Okay. And then when you go to the folder where you keep all your projects, you should have a new folder for that project you just created. In my case, it is smoking tax. Click on that. And I want to drop in the data that I just downloaded into this folder, because R is going to always be searching for files in this folder when I have this project open. Okay. Now in the previous tutorial, we learned how to load in CSV files, comma separated value files. In this module, we will do Excel files, just in case you happen to have Excel files for your data source. So there is going to be another new package for this. It is called readxl. I believe I already have it, but I will run and let it update. Okay, but just like last time, once we install a package, we never need to do that again. So instead, we'll just jump to the next step, which is always to load it in. Library says I want to load in all of the functions that were created for this package readxl. And run it. Alright, I'm going to save my script file. I'm going to call it code. It's going to save right into that smoking tax folder. Alright. Now, readxl is going to allow us to load in an Excel file into our data. So I'm going to do read, and then it's already trying to kind of lead me into which function works here, and read_excel is going to be the one. In the parentheses, we need to tell R what file to add. So we're going to put either quotes or apostrophes, either way. And then the trick is to press tab, and this will pull open all the files in that folder that you could possibly add. And we want smoking.xlsx. Okay. Now if I click run, it will of course dump all of this data right into the console, as our previous tutorial showed. But I want to save it. Now this time what I'm going to do is I'm going to save my initial version of my data as raw. And I'm not going to touch it. Or at least I'm not going to save over that one anymore. That way I always have the original version of the data in my objects, and I can always refer to it if I wish. Okay. And then if I want to do something like our coding is very sensitive to capitalization, and I don't want to press shift all the time. I might as well just make everything lowercase in terms of these variable names. So if I want to do something like take my raw data and rename all to lower, then what I'm going to do is not save this back on raw because I want to just leave that one alone. I'm going to save it as an object called clean. All right, error message. This happens. Well, rename all is a function that is existing within the package tidyverse, which we pretty much will always load in every time we are running our code. So library tidyverse is just going to be a constant for us. Okay. Every time we reopen a new project in R, we need to run our code to bring in our functions. So all of these library commands, we will rerun those. All right, now I run it and it works. So when I look at it, I can verify that yes, it turned those capital letters into lowercase letters, and therefore it will be much easier to code with them that way. Okay. Now often with your data, you're going to want to do a lot more than this, just renaming the variable names in order to start analyzing it. And what I would generally suggest is not to do, it's tempting to do this, right? Take clean and create a new variable called x, and it is whatever, right? And it's tempting to then say just take clean, do something to it, and save it back on itself. But you can skip that step and just keep tacking on additional code into this chunk here, right? This chunk of code says take raw, do this stuff to it, and save it back on clean. And if there's already something called clean, it will just overwrite it. So whenever we want to update what's happening in this clean data, just come back and run this chunk of code, and we'll be good. So maybe when I look at clean, I see that this is the I think this might be mean income in each state, and it's so for Alabama it's 70,000. But maybe I want it to be measured in thousands, not in just dollars. So maybe I want to come in here and say income is equal to income divided by 1,000. Therefore, I get a 70 there for Alabama. And when I run this and check that it's working, there I get a 70.25. It's in thousands. Okay. And any other thing I end up wanting to do with my data, I can just keep going. Pipe and keep adding stuff, or keep transforming variables the way that I see fit. Okay. Now this is going to be a tutorial focused heavily on how we start to show that two variables are related in some way. So one way in which this might happen is that we want to show that there is a relationship between a categorical variable and a continuous variable. So maybe what we want to do is create a density. So maybe I want to show the smoking rates in these different states, this continuous variable, but I want to see how it differs by region of the US. Okay. Let's start by doing this graphically. So I'm going to put 4 pound signs, and then I'm going to put a conditional density, and then 4 more pound signs. That way it shows up here like a table of contents for my work. Okay. Now, maybe I've kind of forgotten how to get started with coding a density, right? But we know that we did it in the previous project. Now, we could click this little drop down arrow in the top right corner and click on universities and try and go see it. But there's almost a quicker way and an easier way, because then we'll have to close out of this project, open a different one. The easier way might be to go back into your folders, click into that universities project, and then double click code.r for it. This will open our code from our previous project. Okay, and therefore I can go back in and see, oh yeah, if I want to do density distributions, I start by saying, here's the data I want to use, and then, yeah, ggplot, that's the one, right? Okay, so maybe I'll move this all the way to the right to not get confused. We have 2 code.rs. So I want to take my clean data, and I want to take ggplot, and And then I can't remember what goes inside of it, so, oh yeah, it's called AES, which stood for aesthetics. Okay, so aesthetics, and then it's going to ask, what do you want X, Y to be? And we're trying to show the adult smoking rate, right? And then whenever we start ggplots, it's always plus to keep adding things, and then geump density would do the trick. Okay, let's run it. Okay, so there we have the density distribution for adult smoking rates across all 50 US states and Washington, D.C. But we really want not just a density, we want a conditional density. So we want to know, what does this line look like if we separate it out by the region of the US. So X is the adult smoking rate, and the way to actually do this is just to set a color. Say, do things separately, or give separate colors, separate colored lines for each region of the US. We can run that, and there we got it. Okay, now a lot of times with densities, fill typically works better, visually at least. So if we switch color to fill, this will say fill underneath of those densities with the color separately by region. So that kind of did the trick for us there, is to put into the aesthetics. Aesthetics is just telling ggplot how to define the x-axis, and then how to decide how to fill underneath of the lines. And it says fill it by region. So do it separately by region, give us a separate density for each region. Now there's a couple of things that we might do. So like over the course of the semester, we're going to start trying to make our graphs look professional and pretty. So one way to do something better with this graph is actually to take that the legend where it says Midwest, Northeast, Southwest, and move that to the bottom of our graph, because we kind of want to have more of an x-axis so we can see more stuff. Okay, now legend position bottom is going to do the trick for us here. Turns out a lot of the ways in which you can customize your plots in R are just adding things into theme. So legend position equals bottom is going to do the trick. How do I know that? The first time I ever had the thought to move the legend to the bottom, I didn't. Right? This is a good use for Claude or ChatGPT to ask, how can I move that legend to a different position? Right? Let's see why this is an improvement. Let's run it. All right, so now we can actually see more of the distribution on these densities, because the x-axis is allowed to take up the full scope of the graph here. So I think that works much better. Okay. But we're not done yet. I want to do a couple more things with this to make it more intelligible for the viewer. All right, so the first is going to be to set the transparency underneath of the curve so that we can actually see where this red density keeps going. Does the line just keep going like this, or does it come back up somewhere and it's just hidden? If we set alpha to be the transparency, this might help us see it a little better. Okay. All right, now this visual really only works because there's only 4 different categories for the actual regions of the country. If I was to do this with a categorical variable that had a lot more different categories in it, then the whole thing would be a mess. So 4 categories is probably about the max that you would want to do. But with 4, I think we still can get enough information from this conditional density plot. All right, next. I want to do one more thing to make this look just a little bit better before we call it good so far, which is a viewer will look at this and say adult rate, and they don't know what that means, right? So let's go in and add labels. So labs is what's going to do the trick, plus labs, and this is where you're going to tell ggplot what to call these things. So x equals adult smoking rate, and then y, this is just a density, so we don't need to do anything too special there. And then the last thing is any aesthetics that you define, you can also label those. So fill should be equal to, I mean, region is good, but I want a capital letter on region there, so fill is region. Okay. The last thing then I want to do, because I'm going to start getting picky here, is 15. I wish it said 15%. So if we go and ask Claude how to do this, let's ask Claude. So in a ggplot with the x variable as a smoking rate, how can I make it be in percents with percent signs added? There we go. It says use scale x continuous and then labels percent. I'm just going to add just this one line because we've already got all these aesthetics defined, right? So scale continuous percents. All right. Got another problem. This tends to happen. 1500%, what's going on? Well, in our clean data, it's already got this in percent. So typically, R will associate 0.2 with 20%. Instead, we have 20 as already 20. It's like it's already in full percents, right? It's not as a fraction. It's not 0.2. If it was 0.2, it would do a better job with this. So all I want to do here is, well, there's two ways. I could come back up here into this chunk and add another pipe and rescale my variable for smoking, but instead I just want to do it here because I don't want it, I only want to do this for this graph. I don't want to do it and make it be 0.2 in my clean data, just for this graph. So after the pipe, I'm going to press enter and mutate that adult rate equals to adult rate divided by 100, and then pipe all the way to my ggplot, run that. Much better. Now I've got the values that I want because I've rescaled the smoking rate to be 0.2 instead of 20, for example, by dividing by 100. Last thing before we move on, if you want to easily get this graph into an Excel file or into a Word document, the easiest way is not necessarily to take a screenshot, just click export and copy it to the clipboard. If you want to change the heights and the widths, you can do that. Like 800, update the preview. Now, the size of the text might not follow with this rescaling, so be careful that everything is still readable, but I think this looks pretty good right here, so I might then copy the plot. And now it's ready to go. I can just paste it in a Word document. Okay, that looks great. Later on in the course, we'll learn how to automatically set all of these colors. Maybe you don't love the olive green, that's fine. We can reset all that. Later in the semester, we'll do that. If you're super ambitious and you want to already do it, ask Claude, ask ChatGPT, and they'll help you with that. Okay. Next, sometimes these densities show way too much information, so maybe instead what we want are just conditional means. I just want to know how the average adult smoking rate differs across these different regions. Okay, so here is what we know so far. We can take clean and use summarize. Summarize will give us the mean of our variable that we want, right? So if we run this, boom, it says on average a state has a 16% adult smoking rate. But the problem is it's not conditional, right? This is just mean of all of my states. It's not the means within each region. Okay. Well, the way to do that is after your first pipe, put in what we call group by. Right? And this says group your data into groups by whatever variable you tell us. So if you do group by region, and don't forget to pipe to the next thing. Group by region says lump every state by the values of region, categorical variables. So take all the Midwest states, lump those together, and then calculate the mean smoking rate within each of those. And then we get that southern states have an average smoking rate of 18%, Midwest 17%, and Northeast 14%, something like that. Okay. And that will give us our conditional means. Of course, we can also get more than that if you want. We can get the maximums within. You can get conditional maximums, conditional medians, conditional standard errors, or standard deviations, whatever you want. But group by is your ticket. Okay. Next, suppose we want to do two continuous variables. So we want to see not how region and smoking rate are related, but maybe we want to know how cigarette taxes are related to smoking rates. A scatter plot is a good place to start here. So I'm going to say I want to use my clean data, and then I want to create a new plot. Now, with a scatter plot, we do need to define what is the x variable in the plot and what is the y variable. So the x variable here should always be whatever you think causes the other thing. So like I have a theory that cigarette taxes will affect how many people will be smoking. Or like I have a theory that the weather outside will affect how many people eat ice cream, not the other way around. There's no sense in thinking that people eating ice cream causes it to be warm or something, right? So your project will have a similar style to it where you think some variable, we always call that x, has some kind of causal relationship where if this one changes, it probably causes y to change as well. So in this case, putting adult smoking rate here. Okay. If I just press run, it says here you go. Here are the axes, but like what should we put on this thing, right? So again, we press plus, and this is where we go to our geometries. And with an already defined x variable and y, geom scatter, it's actually called geom point, and I know that because it didn't let me type in geom scatter. There's nothing there, right? It didn't give me any suggestions. It's a dead end. Geom point is what it's called. Let's run this. Okay, and then we get points where every one of these black dots represents a row in our data, right? So there's one state that has a $2 cigarette tax and 15% of people smoke. One state, boom. Okay, so this graph really works well to just show all of your data at once, really. That's what it's doing. Okay. There's a few ways to play with it. You can set the size of the points. You almost have to just experiment. 10 is insane. 1 is maybe a little too tiny. Let's go with 2. Okay, I think that looks fine. Sometimes they overlap, especially if you have a lot of data. So maybe you want to set this equal to like 0.7. That way, if these 2 points are together, then the viewer of your data can see that there are actually 2 points there, not just one. So that can help. We can also put a color on it if you wish. Maybe we can't remember our colors, so colors in R. And then, there's some color that just gives us a lot of joy, so we set that one, I don't know, sea green for. But choose whatever makes you happy. Okay. So it's a good start. Next, I want to get serious here and label these things. So x equals cigarette excise tax. I'm even going to tell the viewer of my poster it's in dollars. Actually, no, I'm not going to do that because I'm going to just go and make it look better later on. I'm going to put dollar signs on the thing by asking Claude, y is adult smoking rate. Let's make sure this works before we keep trying to do other stuff. There we go. Looks good. Okay. All right. Next, I want to go back and I have a theory. What if we, in order to get percents on the y-axis there, do scale y continuous? Let's see if that works. It does, but of course we get the same problem where we need to rescale. That's fine. Great. Now I forgot how to put dollar values on the x-axis. Oh, but I had it, right? I had it in my last code, so we can always go back, scale x. But I don't want to do log 10. I think I got the patterns down. Plus, let's do scale x, not log 10, but on a continuous scale. Oh no, couldn't find a function. That always means, couldn't find a function, always means you're missing some library that you didn't load in. In this case, it's scales. If I didn't know that, I could always go ask ChatGPT or Claude, which package haven't I loaded in here, and it'll tell you that label dollar comes from scales. So when I run scales, I load in all that stuff, and now we run it. There we go. That looks pretty good. Okay. Now the next step, something we could do with the scatter plot to even take it a little further in terms of showing how these two variables are related to each other, is to do a geom and then add in what is called smooth. Okay, let's just run it like this first. Remember to keep adding pluses after every one of these additions. Okay, now what it gives me first is what is called the lowest curve. This means essentially R is drawing in a blue line that it thinks does something like minimizing the squared errors, distances from these green points, but there's no shape, so it can just go all over the place in order to try and make that happen. We generally don't love these because it does weird things, like it predicts that as you raise cigarette taxes a little bit, say from 25 cents to $1, people will smoke more. It doesn't really make sense. It's probably just a weird data thing, random variation. So often we come in and say, actually make the thing a straight line. So LM means linear model. So this blue line will correlate perfectly with what R would estimate in a linear regression. So method equals LM. Okay. The standard errors are shown with that band there. We don't know what those are yet. That's okay. I want to turn them off anyways. I just want to see that blue line there. And then we can also change the color of it to match our fancy. Let's do purple 4. Okay, great. So now we can see the relationship between adult smoking rate and the cigarette excise tax rate, at least in terms of a linear model with a straight line. And there we go. All right. Now at some point, we surely just want to actually regress these two variables. So we actually want to get the numbers, not just that purple line in the graph there. So we might actually do simple linear regression. Get actual estimates for the slope of that purple line. What does happen when cigarette excise taxes go up by $1? Okay. The function is LM. Okay, so LM is linear model. It tells I want to relate these two variables together, and the code that goes along with it looks like this. It says, put in your Y variable. So for mine, it's called adult rate. Adult smoking rate is what it is. Right? Your Y variable, and then you put this little tilde here. It says explain. It means explained by. So I want to know how adult smoking rates are explained by cigarette tax rates, comma, and then you tell R which data set you're trying to use here. And if I use raw data, for example, it'll tell me these things don't exist because it's case sensitive, right? And so I actually just want to use the clean data. Okay. And then when you press run, it'll give you the coefficients that you're after in terms of both the intercept terms, as beta 0 hat and beta 1 hat, the estimated effect of a $1 increase in cigarette excise taxes. Okay. But we can also get a lot more out of our regression results by saving them back on something. Okay, so I'm going to save it as an object called OLS and run this again. Now if I look at it, it's kind of it's a big list of a bunch of things. So like, for example, all of my residuals are listed in here, the coefficients show up here, but it's not a very efficient way of looking at this. So what I'm going to do is go back and install a new package, which is called JTools. So install packages, I think it's called. Okay. Before I can use any of it, I gotta add it in as a library and run that one. Built under a previous version, that's fine. Okay. Because then if I do sum with two m's and then put in the results that I want to summarize, OLS, now I get a better looking table. It says, here's your intercept term, 19.28, which tells us something like it projects that if a state has no cigarette taxes, 19% of adults will smoke, 19.3%. And then here's our beta 1 hat. For every dollar increase in cigarette excise taxes is associated with a 1.63 percentage point decrease in adult smoking rate. We get an F statistic. We don't know what this is yet. That's okay. We get an R squared of 0.35. So 35% of the variation in a state's adult smoking rate can be explained by its cigarette excise tax rate. It gives us an adjusted R squared, which we don't know what that is yet, so that's okay. But this will be a better way of looking at our actual regression results by using sum, which comes from JTools. Okay, so I might even make myself a little comment here, right? It says library JTools. So this comes from, I'm going to do it this way actually, JTools package to run sum. So I don't forget which actual library I need to run in order to use that function to show all of this. Okay. Now here's your stopping point for the Module 3 homework. So press pause, and then once you get to your Module 4 homework, come back, press play, and we'll take off from here. Okay, now for your Module 4 homework, you will find your standard errors for your regression coefficients right here in this table. They'll be used to calculate these t statistics, and their corresponding p-values for each of your variables will show up here as well. So that will be the way in which you can get those. Okay. Now sometimes you might want to say run a regression where you need to rescale one of the variables. So let me show you what I have in mind. So if I do adult rate as explained by, let me go back and check my variable names again, income. Okay. Clean. Now right now I have my income variable measured in thousands of dollars, right? So this is 70,000, this is 108,000 in Alaska. So what this is showing me is if income goes up by 1, but that really means income's going up by $1,000. It's going up by 1 in our terms, but it's $1,000 in like real interpreted kind of terms, right? But $1,000 is actually not that big of a jump for a state's average income, considering like Washington D.C. is 138 and Florida is 75, right? So maybe I want it to be in tens of thousands of dollars. Okay. Now this is going to be a case where we would want to do something like this, right? So rescale variable for regression. Now I actually want to do clean and pipe and now do the rescaling, kind of like we did on this conditional density. And I want to take income and divide it by 10 again, right? And then do the linear model from there. Now, if I say, okay, take the clean data and then do something with it and then run a regression here, I don't really need to say use clean again as the data. I can just put a period which says, or you can do data equals period, which means just use the data that we're already, you know, piped in. Okay. So we run that, and looks no good because why is this? So we've got adult smoking rate. Oh, my mutate is a problem, right? So I didn't define the new object, right? So it needs to say income equals income divided by 10. That's the problem. At least I thought. Let's try this. Formulas are different. Well, sometimes you get to this point and it's time to ask AI. Here's my code. Here's the error message. What's wrong? Okay. So it says, alternatively, you can do this. Clean, pipe, mutate, pipe. Huh. I thought I had exactly this. So let's see if we can find any differences. None. Interesting. Let's try this one. This one worked, although I don't like this. So I wonder if I could do something else. So what if we instead go like this, okay? LM income and the data is, so I'm just gonna put clean. Data equals clean, or just say clean, that's fine. Okay, this will work, but I don't have it scale. I don't have it scaled. It should be negative 1.4. That's $10,000 increase, right? So I think I can do this. Good. So if you ever want to rescale a variable within a regression, you can do this. You can say I, you can put an I in front of it, and I means I want to do something to this variable. I can even like square it in here or something, right? I can do this times this. Later in the class we'll talk about why you'd ever want to do something like that, but here I just want to divide it by 10. Just means I want to actually do something to this variable before I make it a term to use in the regression. So, haha, we found it. And that's even easier than the thing I originally coded. So, this is a good way to do this. And I can save it back on OLS. Maybe I'll call it OLS2 so I don't overwrite my previous regression results that I have. And then I can take a look at my results. So, this one says, on average, if a state's income increases by $10,000, then this is associated with a negative 1.44 percentage point decrease in the adult smoking rate. Okay. Now, we can always use dummy variables for x variables here too. They're just ones and zeros, so R will calculate coefficients the same way. It's just a fancy way of taking conditional means, so dummy variables can go anywhere in here as long as they are ones and zeros. They are good. Now once you're done with your project, click save on your script file, and then we are ready to close it out. You can always just leave it open as well, whatever makes you happy, but if you click close, then sure, we'll just save the data here, and then we are good to go.